Hi everyone, this is Dr. G. Ravindranath Reddy working as Assistant Professor of Mathematics in MLR Institute of Technology, Hyderabad. So we are discussing numerical methods and integral transform course. In that we are at the first shifting theorem in inverse Laplace transform. So in this video we are going to discuss first shifting theorem in the inverse Laplace transform. So where we can use this first shifting theorem in the inverse Laplace transform, and what are the uses of first shifting theorem in the inverse Laplace transform. So first we will take the statement here. So if L inverse of f bar of s is equal to f of t, then L inverse of f bar of s minus a is equal to e power at into f of t. So this is the statement here. So we have another statement for this shifting theorem here. We can take it as L inverse of f bar of s plus a. So whenever the function is in terms of s plus a, then that inverse Laplace transform is given by e power minus at into f of t. So these are the two statements of first shifting theorem in the inverse Laplace transform. If the function is in terms of s minus a, then we can take the inverse Laplace transform as e power at into f of t. So if you have a negative sign here in the function, then the power of that exponential function must be a positive. Suppose in the function, if you have a positive sign, then the power of that exponential function must be a negative power. Okay, now we'll see how to prove this condition here. So while we are discussing the first shifting theorem in the Laplace transform, we have proved the condition that Laplace transform of e power at into f of t. So we have proved this condition, e power at into f of t. For this function, the Laplace transform is given by f bar of s minus a. So now you send this L to this side. So you will get L inverse of f bar of s minus a is equal to e power at. If you send this L to this side, it becomes L inverse. L inverse of f bar of s minus a is given by, what is the remaining here after sending that Laplace transform to that side? It becomes e power at into f of t. So from the definition in the given statement, f of t can be written as L inverse of f bar of s. So you can take e power at into L inverse of f bar of s. So the main thing is L inverse of f bar of s minus a. We can take this value is equal to e power at into f of t. That f of t can be written as L inverse of f bar of s. So this is the first shifting theorem in the inverse Laplace transform here. Now we'll take some examples where we can apply this first shifting theorem in the while you are finding the inverse Laplace transform for the function f bar of s. Let us take some examples for this. Now this is our problem. So L inverse of 1 by s plus 2 whole square plus 16. So in the previous video we have seen how to find out the inverse Laplace transform using partial fractions. Now, so whenever we are having the denominator in the f bar of s, suppose if the f bar of s, suppose imagine that this is the f bar of s here. So s by s square plus 5s plus 6. So now the denominator is a quadratic polynomial or quadratic expression in terms of s. So if this is reducible into a linear factor, then we can go for the partial fractions and we can apply L inverse on both sides after splitting into a partial fractions. Suppose if the given denominator is in the polynomial of quadratic polynomial, and if this denominator, if this quadratic polynomial is not reducible into a linear factors, whenever the given polynomial is not reducible into a linear factors, then we can take the help of this first shifting theorem here. So that is the main use of first shifting theorem. Once again I will repeat this. Whenever the quadratic polynomial in the given f bar of s in the denominator, if that polynomial is not reducible into a linear factors, then we can convert this function in terms of f bar of s plus a or in terms of f bar of s minus a. So whenever this is not reducible, so that means irreducible into linear factors. If it is reducible into linear factors, then we can go for the partial fractions and we can find out. Suppose if the given quadratic polynomial is not reducible into linear factors, then we have to take the help of this first shifting theorem here. Now let us take this example here. So this is already it is given in the standard form. So in place of s here we got in s plus 2. So this entire function I want to consider this as L inverse of f bar of s plus 2. So by using whenever the function is in terms of s plus a or in terms of s minus a, then for that function if you want to find out the L inverse Laplace transform, then we can take the help of first shifting theorem here. Now use the first shifting theorem here. So what is our first shifting theorem? L inverse of f bar of s plus a is given by e power minus at into f of t. So this f of t can be written as e power minus at into L inverse of f bar of s. This is our formula. So in place of a, here we are having 2. So replace e power minus at with e power 2t. And L inverse of f bar of s. So here wherever we are having s plus 2, you replace that s plus 2 with s. So since here in place of s here we are having s plus 2, so we have taken the function as f bar of s plus 2. Now replace this s plus 2 with s, then we can get our required f bar of s value here. So if you replace s plus 2 with s, you will get 1 by s square plus 16. So now this can be written as L inverse of 1 by s square plus 16 can be written as 2 4 square. This is of the form L inverse of 1 by s square plus a square. So yesterday in the previous videos, we have seen the formula for L inverse of 1 by s square plus a square, that can be written as 1 by a into sin at. Now here in place of a, here we are having 4, so this can be written as 1 by 4 into sin 4t. So the main use of this first shifting theorem is, in the given f bar of s, in the given function f bar of s, if the denominator is not reducible into a linear factors. Suppose if the denominator is in the quadratic polynomial, if that quadratic polynomial is not possible to reduce into a linear factors, then we can convert that function f bar of s either in the form of f bar of s plus a or in the form of f bar of s minus a. Then we can use the first shifting theorem to find out that L inverse value here. So we will go for the next example here. So now let us take this problem. L inverse of 3s minus 2 by s square minus 4s plus 20. Now first you concentrate on the denominator and check whether that denominator s square minus 4s plus 20, is it possible to split into a linear factors or not. If it is possible to split into a linear factors, then we can apply partial fractions and we can find out the L inverse here. Suppose if the given quadratic polynomial in the denominator, if it is not possible to split into a linear factors, then we have to take the help of this first shifting theorem. Now let us take this. So L inverse of 3s minus 2 by s square minus. So it is not possible to split into a linear factors. Now what I want to do is, the denominator I want to convert either in the form of s plus a or in the form of s minus a. So here we have to check s square minus 4s. So these two terms must be, we have to get in this expression. So I want to take this denominator here, For the product of two terms here we are having a negative sign, so we can apply either a plus b whole square formula or a minus b whole square formula. So now out of these two, if you want to identify the suitable formula, now here we are having minus sign. Thus this is of the form a square minus 4ab plus b square. So this you will get in this a minus b whole square form. So now you take this one s square, we can take it as s minus, you take off of this constant coefficient, this coefficient 4, that is 2, s minus 2 whole square. So if you expand this one, we in this expression we have to get s square minus 4s. If you expand this, so this the expansion of this one is s square, so minus 4s plus 4 a minus b whole square form. So now s square minus 4s, we have to get these two terms as usual according to our given expression. So once if we get s square minus 4s in this expansion, then whatever we have taken s minus 2 whole square is correct. So but here the constant, once if we observe this constant term, if we expand this constant, this s minus 2 whole square, you will get the constant term as 4 only, but we want 20, so we are shortage of 16, so we have to add 16 for this 4, you will get this. So once if you simplify this expression s minus 2 whole square plus 16, once again you will get, we have to get the previous denominator, that is s square minus 4s plus 20. So the main important thing is, whenever we want to convert this quadratic polynomial in terms of s plus a or s minus a, then we have to concentrate on these two formulas, a plus b whole square or a minus b whole square. Suppose if the coefficient of s in the given polynomial is negative, then you go for a minus b whole square form. Suppose if you have a positive sign for the coefficient of s, then we can choose a plus b whole square formula. According to that, we have to convert. So now the entire denominator is converted in the form of s minus 2. Now the denominator is in the form of s minus 2. Now go to the numerator. So in the numerator we are having a function in terms of s, but whereas in the denominator we are having s minus 2. So here we are having s minus 2, in the denominator we are having only s. Now immediately what we have to do is go to the numerator. So our numerator is 3s minus 2. So 3 into, in the numerator wherever we are having s, replace that s with s minus 2 immediately. So s minus 2. Now simplify this. So you will get 3s minus 6. But in the numerator we are having 3s minus 2. Okay, so here we are having 3s minus 6. Now our task is we have to convert this minus 6 into minus 4. So this is possible only by adding 4 in the numerator. So now simplify this, 3s minus 6 plus 4. So you will get 3s minus 2. So whatever the denominator you get, we have to convert that numerator also in the same as in the denominator. So now you convert this. So 3 into s, we have replaced s with s minus 2 because in the denominator we are having s minus 2. So 3 of s minus 2 plus 4. If you simplify this, you will get this value here. If you simplify this, you have to get the denominator. So now once if you observe this entire function, so the entire function here we are having in terms of s minus 2. So we can convert this entire function as f bar of s minus 2 because in place of s here we are having s minus 2. So once if we observe this L inverse of f bar of s minus 2, this is of the form L inverse of f bar of s minus a. So you can find this formula only in the first shifting theorem. So what is our formula here? E power at into f of t. So this f of t can be written as e power at into L inverse of f bar of s. So this entire value we can take it as f bar of s minus 2. Now if you want to get f bar of s value from f bar of s minus 2, just replace s minus 2 with s. you will get our f bar of s value here. So now this is of the form a plus b by c. So separately you apply a plus a by b, a by c plus b by c. So you take 3 common here. So 3 into L inverse of first term by denominator plus 4 into L inverse of first term by denominator. So here apply the first shifting theorem here. By applying first shifting theorem, so by applying the first shifting theorem, so whatever the function we are having in terms of s minus a or s minus 2, we'll convert this function in terms of s by using this first shifting theorem. So this can be written as 3 into e power 2t into L inverse of, replace s minus 2 with s, you will get s by s square plus 4 square plus 4 into e power 2t into 1 by s square plus a square, s square plus 4 square. Now here directly we are having the formula e power 80 into, this can be written as, so we have the formula L inverse of s by s square plus a square. So we can take this value is equal to cos 80, and here we are having one more formula, that is 1 by s square plus a square, this is equal to 1 by a into sin 80. Now use these formulas, so you will get this value. Finally this is equal to 3 into e power 2t into, this can be written as cos 40 plus 4 into e power 2t, and this can be written as 1 by a, that is 1 by 4 into sin 40. This 4 and 4 gets cancelled, you will get our required value here. So the main important in this example, it is very clear that we can say that by using this example we can see where we can use this first shifting theorem clearly. So this denominator is not possible to split into a linear factor. So whenever we are having this type of situation in the given function f bar of s, then we can convert that quadratic polynomial in terms of f bar of f, in terms of s minus a or s plus a form, and then we can apply the first shifting theorem here. Now let us take one more example here. So L inverse of s plus 3 by s square minus 10s plus 29. This is our problem. So here our f bar of s is equal to s plus 3 by s square minus 10s plus 29. So now you concentrate on the denominator first. Our denominator is a quadratic polynomial in s. So now you check whether this is reducible into factors or linear factors or not. So s square minus 10s plus 29. This is not possible to split into a linear factors. So now immediately what we have to do is, for the coefficient of s we are having a negative sign. So we have to apply a minus b whole square formula. So here a is nothing but s. So s minus. So how can you get this one here? You take half of the value here. Half of the value for 10 is 5 whole square. Now if you expand this s minus 5 whole square, these two terms must come in this expression. So s square minus 2 into a into, so this can be written as a square minus 2ab plus b square. So minus 2 into a is s into 5, that is 10s plus 25. So s square minus 10s plus 25. So here these two terms must be in this here. So s square minus 10s we are having both terms, and only the constant term is changing. So here we got 25, but we want 29. So for this you add plus 4. So this s square minus 10s plus 29 we can write in the standard form. So like this we have taken. So once after converting the denominator in the form of s minus a or s plus a, then immediately go to the numerator What is our numerator here? S plus 3. So wherever we are having s in the numerator, replace that s with this s minus 5. So s minus 5. But in the numerator we are having s plus 3. We should not change that numerator which is given in the problem. So but we can rewrite that numerator. So s minus 5, but here you want s plus 3. So we have to add some constant value 8 in order to get this value is equal to plus 3. So this is the way how we can take. Now you for some time you consider this s minus 5 as a single term and 8 as a single term. This is of the form a plus b by c. So this can be written as a by c plus b by c. So similarly you apply. So first term by denominator plus second term by denominator. So since here this entire function is in the form of a bar of s minus a. So for this we are applying the L inverse value. So we have to take the help of first shifting theorem. So here this can be written as e power at into f of t. So here a is nothing but this constant. So this can be written as e power phi t into f of t. F of t can be written as L inverse of a bar of s. So how can you get this f bar of s here? By using the previous this function which is in terms of s minus a, s minus 5, replace that s minus 5 with s, you will get our f bar of s value. In both cases this is the procedure we have to follow. Now use the standard formulas. This is L inverse of s by s square plus a square, and this is L inverse of 1 by s square plus a square. Use these formulas, you will get our required value here. So this is the way where we can use this first shifting theorem in the inverse Laplace transform. So in this video we have seen how to use the first shifting theorem in the inverse Laplace transform to find out the inverse Laplace transform for the given function whenever that denominator of that f bar of s, whenever the denominator of the given function is not reducible into a linear factors. And in the next video we are going to find out inverse Laplace transform of derivatives. So where you can use this inverse Laplace transform of derivative concept. So how can we use this in order to find out the L inverse for the given function f bar of s. Thank you.